G'day Year 12 Method students. In this video we're going to go through a bit of an extended response question. This section's on applications, and applications and worded problems typically are extended response questions. So with sine and cosine functions, they can model lots and lots of different things in real life. Basically anything that kind of oscillates or bounces up and down. So sound waves, rising and falling temperatures, tide depths. You've probably seen lots of these in Year 10 and 11. Lots of questions about things going up and down according to sine or cosine functions. And this is just another one that we're going to look at here. So in this example, we're told that a city in the Northern Hemisphere has been considered as a host for the 2024 Summer Olympic Games. And one of the factors being assessed is the temperature for that particular city. The average daily temperature in this city is predicted by the function C. C of t is equal to 20 minus 5 cos of pi t on 183, where C is the temperature in degrees Celsius and t is the number of days from the start of the year. The first thing that we're asked to do is to state the amplitude in the period of this function. Now, we're treating this as a calculator question. Extended response questions typically are on methods exams. But we're probably not going to need to go to the calculator for the first part of the question. The amplitude, and we've got to be a little bit careful here because the constant is written at the start rather than at the end. The amplitude here is just 5, right? That's the coefficient of cosine there. So the amplitude, we can just read straight from the equation, is 5. Remember that we give it as a positive number, even though the coefficient is negative 5. Period, well, there's a little more work to do for the period. Remember, the period is 2 pi over n, which in this question is 2 pi over or divided by pi on 183. And that's really going to be 2 pi times 183 on pi. And with pi's on the top and the bottom cancelling out, that's really just going to be 2 times 183, which is 366, which is how many days in a leap year, which Olympic years are leap years. So, well, most of the time. So our period is 366 for this question. Okay, those two things are going to come in handy because the next part of the question says to sketch the graph for one complete cycle, which is going to be 366 days, starting from t equals 0. Label all intercepts, poorly written question here, label all intercepts. Well, that probably, what was I thinking there? I was probably thinking endpoints. Label all intercepts, endpoints and maxima / minima with their coordinates. All right, so let's get stuck into it. We're going to draw, well, what do we got? We've got an amplitude of 5, a mean position of 20. So our values are going to bounce up to 25 and down to 15. I'm going to make the y-axis here get a little bit creative and just do this at the bottom. I'm actually not going to start from 0 just because I want to make the curve really clear. That could be my x-axis. I should be using a ruler. All right, so I'm going to call this value 15 on my y-axis. This will be 20, and that'll be 25, and my whole graph really is going to exist between those two values. All right, what have I got? 1, 2, 3, 4, 5 kind of grid points along my x-axis. 366 days in the year. Let's see if we made it go up to 400 just to be sure. What could I do there? Each of these could be 80. That seems reasonable. 80, 160, 240, 320, 400. Often a friendlier question will give you these values marked along the scale already. We've just had to come up with it ourselves, but that seems like a reasonable scale for this question. Okay, this is a bit of a line ball call as to whether we would try to do the graph by hand, because it might be simple enough with all this information here for us to just draw the graph without the calculator. However, I know from reading ahead that later on in the example I'm going to need this equation in my calculator anyway, so I'm going to get the graph of it up on my CAS now, just so I can make sure I get my sketch right. So let's put in our rule. The rule was 20 minus 5 cos of pi t, but I'm just going to use pi x over 183. And I'm going to bring up the graph screen here, making sure I'm in radians mode. Right, so dragging onto my graph with that default zoom, can't see anything, but I know from what we've had to think about here, where to look for my graph. Rather than just hitting sort of zoom in and zoom out, I like to, in most cases, set the window. I know I need to see x values all the way up to about, well, I need to see them up to 366, but I'm going to set that up to 400 just to give myself a bit of extra room at either end. My y values, I want to see from about 10 to about 30. Again, just giving myself a little bit extra on sort of either side there. And there I can see one cycle of my graph. So that gives me a pretty good idea of what's going to go onto my piece of paper here. analysis, and then gsolve will give us all the kind of key points. So we might want to start with that y-intercept there. Again, we could have worked this out without the calculator, but the y-intercept is actually at a minimum for this curve, so that's y equals 15. You can mark that point on the graph here with coordinates of 0, 15. The question did tell me to also label maximums and minimums, so let's go analysis gsolve and then maximum. All right, you can see we've got the coordinates of 183, 25, so I'm going to mark that on to my graph. 183, what have we got? That's 160, that's 240. I haven't done a great job here, that's 200. So we've got 183 and 25. And then minimum, I can get that with analysis gsolve and then min. I don't want that one again. Just going to tap across to get this one over here, which happens to be the endpoint, the end of the domain. It's 366.15. All right, and now my job is to draw the curve as best I can. We'll get there, but we've got our graph now. Okay, and once you have the graph, you can often use that to kind of help consolidate and picture what's going on for the rest of the question. So I'm going to keep this graph in mind and just keep it here handy. As we go to the next page, the question says, after how many days to the nearest whole number will the predicted average temperature first be 19 degrees or first reach 19 degrees? So to the nearest whole number, that phrase gives away a little bit here. That suggests that we're going to have to use our calculator to find a value and then round it. So what we want to know is when C equals 19 degrees, T equals what? Basically, that's what we're thinking of here. So we're actually going to solve, and if this was a 2 or 3 mark question, we would need to show some working out. We're going to say, we're going to let C equal 19 in our rule, and then solve it for T. But of course, we're going to get our calculator to do the solving here. Now, given that we don't need an exact value because we're being told to round to the nearest whole number, I reckon we can do this from our graph, but we could also do it using the main screen. So if we were doing it graphically, we could say it's analysis, gsolve. Now in this question, we know the y value and we're trying to work out the x value. We're trying to find the value of t. So we could say, all right, when we want to find the x value, we do xcalc. We put in the y value, which is what we know is 19 degrees. Hit OK, and that point gets highlighted for us on the graph, 79.77. So t equals 79.77, which to the nearest whole number would be 80 days. Of course, I'll just show this anyway. We could also have up here said action advanced solve 19 equals this. The disadvantage of this method is that if we don't put in a domain at the end here, we're going to get a general solution, and that's typically, not what we want for an application question. So just show you to remind you, if you haven't seen this little trick already, our domain, so given that x was between 0, so 0 is less than or equal to x, and x is less than or equal to 366, and I'll pop this in decimal mode because we wanted to the nearest whole number, we get, okay, 286, which is actually where it gets back down to 19 over here, but the 79.7 is this first value that we wanted here. So 2 different ways of getting that answer. Probably in this question it was easy to do on the graph, but good reminder of how to do it from the equation up in the main screen. Okay, next question, what is the predicted average temperature at the end of January, i.e. when t is 31? So really what this is doing is just asking us to sub in t equals 31. You can do that with function notation. We can say this is just c of 31. Again, you might need to show working if the question is worth more than 1 mark. So even though you're going to get the calculator to do everything for you, you often have to write down a step like this just to show how you're generating your answer. All right, and then we'll calculate it. So given this one's not a solve, I'm going to do this one up in the main screen. So we're just taking what we have to start with, 20 minus 5 cos of all the rest. And I'm just going to change the x to 31. And that's 15.69. Oh, actually, it's at 2 decimal places. Yeah, next digit's the 1. So 15.69 degrees. All right. Last question. Organisers would like the game to be scheduled at a time where the average temperature is predicted to be between 21 degrees and 23 degrees. At which time of the year could the games be scheduled in this city? Okay, so what we need to do, and this is where we're going to go back to our graph, is we need to look for when is the temperature going to be between 21 and 23 degrees. If we do look back at our graph that we sketched, so 21 degrees is here on the y-axis, 23 degrees is here. And so what we're looking at, I'm just going to do this really faintly on my graph because I don't want to ruin the graph that I've already done, is we're looking for this sort of section of time, right? That's when the games can be held because the temperature is going to be between 21 and 23. Or of course that happens again over here as well, right, in between those two values. So on the calculator, what I really want to find is the coordinates of these points, or specifically the x coordinates of those 2 points, because I want to know when we can hold the games. Right, so let's go to the graph on our calculators. And let's first get the time when, I'm going to use the graph here. Let's get the time using xcalc, because we're trying to find an x value, where we know the temperature is 21 degrees, right, where the y value is 21 degrees. So if we hit OK there, we get 103.229. I'm going to write all this down so I don't lose track of anything. So when the temperature is 21 degrees, T equals 103.229. And it obviously comes back down as well as we looked at on the curve. So T equals 262.771. All right, and I'm just going to do the same thing again for when C is equal to 23 degrees. All right, and find my values of T. So repeat the process, analysis G solve, it's an xcalc, and we're subbing in y equals 23. We get 128.984. And if we tap across to get the next one, that's 237.016. All right, so what we're saying here is that the temperature is between 21 and 23 degrees. Well, if we do a really quick thumbnail sketch, all right, we've got this point here, and this point here, this point here. That's where the temperatures are between 21 and 23. Terrible picture there, but hopefully giving you enough of an idea. And so it's between, in terms of the answer to this question, between T equals 103, to the nearest whole number, and T equals 129. Right, that was when we first went from 21 degrees and then first got to 23 degrees. Or the other interval was when the temperature first came back down to 23 degrees, which is this point here, right, 237, T equals 237, and T equals 262 was when it came back to 21 degrees again. So this point here would be when T equals 263 to the nearest whole number. All right, that's the end of the question. Now it said give the answers at intervals of T rounded to the nearest whole number. So I guess we could say something like, if we wanted an interval notation, T is an element of, well, let's see. We could say 103 to 129 union 237 to 263. And there we go.